So elimination, what are we doing with an elimination? We're going to start with some kind of substrate with a leaving group on it. Then what? Electrons will go to our leaving group. Okay. Now we run into some potential issues. Making a carbocation. I'm drawing this way too big.
Hydrogen. Try to stabilize the positive.
And we have the electrons from our hydrogen come in and make our double bond. Right? That's our generic idea of what would happen with the overall reaction. So let's get a little bit more specific. What are you starting with?
A single molecule.
What's that?
A single molecule.
Yes, we're starting with.
cyclohexanol.
Okay. So if we compare just directly back to our general thing, is that a good leaving group? Okay. Selection negative.
Oh, it creates a strong base.
What happens if it leaves? What would we get? We get our carbocation, and then we get
Strong.
negative oxygen. Okay, and why are we saying that that negative oxygen is now a bad leaving group? Heard a couple people say strong base, good nucleophile. Okay. Ultimately what we're getting at is that that negative charge, not stable. So as soon as it forms, it immediately comes back. Okay. Which then means that step of the reaction does not work. Well, that's problematic because we're trying to do an elimination reaction. Okay. So how can we possibly get this reaction to work?
A better leaving group.
We need a better leaving group. So we can just change the structure. Too bad, can't do that. We need to somehow alter the structure that we've got to make that leaving group better. Okay. So if we think back to what I had drawn up, we had that hydroxide, right? What would make that more stable? Have you seen that structure anywhere? If we put a hydrogen on it, we'd have water. Is water stable? Yeah, that's a really good leaving group. Okay, so I just need to make this OH into water. I can add an acid. Okay, name an acid for me. HCl, thank you for the HCl. So there's our strong acid, which will become relevant in a little bit. Okay. And this is something that you should start focusing on. We've kind of just gone through and said these are our reactions, this is just what happens. We should instead focus on what can happen. So when we look at our HCl, or between these two species, we should immediately say HCl is the one we want to focus on first. Why?
It's better.
Okay. I call it a burn test. Stick your hand in a vat full of cyclohexanol versus stick your hand in a vat full of hydrochloric acid. Well, which one are you going to be a little more nervous about? Probably the hydrochloric acid. Chemistry is focusing on the same thing. Okay, so let's keep our focus there. What makes HCl reactive? The ability to dissociate. The chlorine will take the electrons away from the hydrogen. That means our chlorine is carrying a negative charge and the hydrogen is carrying a positive. Half of my problem is now solved by doing that. To do a reaction, what do I need to do to those charges? Neutralize them. Chloride on its own. How reactive is chloride on its own? Not really. That's why we find it everywhere. Okay? Acid on its own, that's a little bit more reactive. So I can probably ignore the negative chloride and I can keep my focus instead on the positive hydrogen. What do I need to stabilize the positive hydrogen? Electrons. Or a negative charge. Where do I have electrons? Now I can look to my oxygen lone pairs. Those can now share out with our hydrogen, initiating our reaction alone. Kind of make sense? Why pick the oxygen? Well, we mentioned lone pairs, but very often you won't see those specified. What else about that structure might you go, okay, the oxygen needs to be the one? Oxygen is more electronegative than carbon and hydrogen, meaning the oxygen would carry a partial negative, the hydrogen would carry a partial positive, carbon carries a partial positive. Okay. We're trying to neutralize a positive, what do we need to react it with?
The negative.
The most negative thing we've got is our oxygen. In theory, that should be enough that we trigger and go, oh yeah, there's lone pairs, I should draw those. The result, right? So now what? So we keep our focus just like we did on the first case. We need to find our most reactive things. What are the most reactive things?
Oxygen.
The charges. Chloride, we already said, was ubiquitously relatively stable, so we can kind of minimize that. Oxygen does not want to be positively charged. What can it do? It needs to get electrons. It could steal them from the hydrogen, which then means,
Go back to where you were.
what does that mean? Equilibrium. All those fun equilibrium things in 152, we've got a reversible reaction. Where else could it get electrons from? Okay, the carbon-oxygen bond. Why can't it get electrons from the chloride?
Chloride's hot.
If chloride shared electrons, how many electrons would be around the oxygen? It would have exceeded its octet, in which case we'd have to kick a group out. Can hydrogen hold the negative, the extra electrons? Can carbon hold the extra electrons? No. So it does not make sense to break the octet in that direction. So what we'll end up doing is taking the electrons from the carbon-oxygen bond and put them on the oxygen, the single arrow. So far, so good? Now what happened? It's the most reactive thing.
The positive chloride.
Positive charge. And I heard the chlorine. Okay, so what happened? They come together. Exactly right, and we would end up with substitution reaction. What are we trying to do with substitution reaction? No. So something about the conditions that we have chosen for this reaction suck. We need to fix that. We do not want chloride. We need to get rid of the chloride. So we just add H+. Can we add just H+? No, too reactive. It has to be stabilized by something. What could we put in there instead of chloride? Another acid, but the characteristic of that acid must be that its conjugate base is stable. More stable than even chloride. So chloride is still nucleophilic. We need a non-nucleophilic conjugate base acid. Sulfuric acid is the ticket. Why is sulfuric acid generate a non-nucleophilic conjugate base? Why? What atom's holding the negative charge in sulfuric acid? Oxygen. If we looked at stabilizing charge, which one stabilizes charge better, oxygen or chlorine? Chlorine. Chlorine stabilizes the charge better than oxygen. So why is the sulfuric acid better? There's a resonance effect on top of an electronegativity effect that counteracts, or is an additive approach that counteracts the size stabilization of the chloride. So lots of reasons make the sulfuric acid non-nucleophilic. Resonance and electronegativity are two good options. Okay, well, what does this then do for us? Well, I have a positive. We've now said the negative can't react. I still have a positive. I need to neutralize the positive. Where can I find electrons to neutralize it? So now I'm going to have to look within the structure itself. Okay? I could potentially look at the oxygen, but again, that just takes us backwards. Which is still valid, but it just takes us backwards. Okay? So I'm going to have to look for electrons somewhere within the structure. Okay? And this is where I would strongly encourage you to say, Well, I see some electrons, I'm gonna move them. For instance, there's electrons right here in that bond. What happens if I take those?
You make another.
I break the bond, but I'm doing a reaction where I
You won't have
make a
ring.
break bond, so why not? So let's take those electrons. What do we get?
Not a ring anymore.
What's that?
You don't have a ring.
You don't have a ring.
The line structure.
So I've lost the ring. I didn't get rid of the charge. If anything, I made it worse off. Okay. I have this weird lone pair thing hanging out here. What's going on with that carbon?
It's neutral.
It is officially neutral.
So where are those?
It's on the carbon.
What
What orbital? There's an interesting question. What is the hybridization of that carbon?
SP.
SP.
Because there's a hydrogen.
There is an implied hydrogen. So it would still be sp2. How many electrons are around that carbon?
6.
What's the issue with that?
No access on full.
Not an octet. That's an O, by the way. So that reaction, bad idea. So I could continue to try electrons. Why did I try those electrons first? Closest. So we're always going to pick the closest electrons first and see what happens. See how that helps us. Okay. So now let's actually propagate this out to something more useful. We will propagate out to a hydrogen, a CH3, or those two hydrogens. Okay. What do those result in?
Wouldn't you look at the hydrogen attached to the makes the positive charge?
Okay, so let's focus on that one. Let's take those electrons away. What's the result?
No, the octet.
We run into the same issue with our octet. We'd have the lone pair, no formal charge, but missing an octet. Same reason it's bad. That's why we have to go further away. So, what happens?
Form a double bond.
How?
Hold up. Take the electrons from the hydrogen.
Which hydrogen?
I was looking at the one next to the methyl.
Okay, so we can take these electrons,
Take it to the carbon.
swing them down, call that option A. Right, and we have H plus floating off. Any other options?
The hydrogen below the positive charge. So from that.
So we could go down here, call this option B and option C. Those are going to be the same thing. If we took them from the methyl group, what would happen?
You see the octet of the carbon, it's the carbon hydrogen.
Call that D.
You're not showing all your applied hydrogens,
I'm showing all the relevant ones.
Oh, that one.
What's the problem with that one?
Yeah,
Zero
area
charge carbocation.
We have a zero-ary carbocation, unstable. This reaction would likely go massively backwards. Not likely to happen. Is there another way we can move electrons? Rhymes with government. if we took the electrons from that methyl group and we did a rearrangement? We'll call that green A.
Doesn't that make that one positive?
Would that be a favorable reaction?
Still have positive charge.
Still have positive charge. Did we stabilize it? No. In fact, we could make the argument that those are identical structures by just picking it up and flipping it over. Okay. So while that rearrangement didn't really do anything, it is still possible, and that might get us thinking down the next path. Is there another rearrangement we could have done?
Both the hydrogens coming in.
Either set of hydrogens. Right? Versus if we did it over on the other end. I think I heard someone say, oh my God. It's probably a good idea. So we need to come up with ways that we can start to eliminate reactions. Because already we've got, in our blue set, we at least stopped a reaction, but we said this one wouldn't work. B and C are valid, A is valid. Rearrangement A works but doesn't do anything, so we can eliminate that choice. What about B? Rearrangement B. Uh-oh. What was that? It's a more stable carbocation, which says what?
It's possible.
That is actually very likely to happen. If we look at ending our reaction, we're ending the reaction on an unstable intermediate. Okay. If we have an unstable intermediate, is that likely to move to the next step? Not very easily. Which means we are likely to see our rearrangement path being more valid. What about the C rearrangement? So I heard some no's over there. Why?
That positive would rather be next to that.
Less stable? It's still secondary. Does it do anything?
No, it's the same.
There's no advantage. If there's no advantage, would it happen?
No.
No, so not likely. So we thought we were done, and then we advanced found one more step. Yes.
Well, I might be jumping ahead here, but the difference between our A, B, and C versus our B is that you would see a pH change with that, wouldn't you? Because then A, B, and C are freeing up a proton.
In our blue, A, B, and C, you're right, we do see the free up of a proton. In the green, we have no proton freeing up. So we could theoretically say a pH change. But in our green, are we done?
No.
No, so you're premature here. We got to actually make sure that that doesn't free up the proton. So we're now at this tertiary carbocation. Is that stable? It is more stable than the secondary, but is that stable? No, we're still at an elevated energy, so what has to happen? We need something to neutralize that positive charge. How did we neutralize our positive charge before? That looks making a double bond. And we made a double bond by looking for nearby hydrogens. Where do we have nearby hydrogens? There's one. There's one. There's one. Okay. If we go through and look at these results, what do we end up with? Are you saying these are enantiomers?
They could be depending on the chair.
If you turn it, they're the same.
They're the same thing. Without a chiral atom, no enantiomers. Okay. No chiral atom, these are identical structures. Okay. So let's go through and identify our products. So we've got this one, which is the same as this one. So we look at our possible products. That's a possible product. What else do we have?
Double bond at the bottom.
Very bottom. What else do we have?
B and C.
Yeah.
B and C result. So we have three possible products that could come out of this reaction. This is actually why we're doing it. We want to see which of those three products is the correct one. Okay? So that is our goal, in theory, by the end of the experiment, is to say, that was the product that we made. Okay? That's our hope. Okay? So when we run it, we aren't really separating. All we're doing is removing water impurities and all the acid-based junk. We're just getting rid of that, which we can review that material if you would like. Okay. How do we then identify our final product?
IR.
We could use IR. So what does IR show for this first compound?
Ring.
Does not show a ring, because a ring is not a bond. SP and SP2 are also not bonds.
It shows carbon-carbon.
Carbon-carbon what?
The double bond.
Carbon-carbon double bond, yes. What else does it show? Carbon single bond to carbon.
Well, it showed that SP3.
Carbon to hydrogen, SP3. What else? Carbon to hydrogen, SP2. Anything else?
Now, why won't it show the aromatic ring?
It's not an aromatic ring.
Oh, because it doesn't have the.
For it to be, and I keep dodging because everybody keeps asking me about aromaticity. Aromaticity is officially a second semester topic. To be aromatic, focus on just benzene. That's all you really need to know for this semester. Next semester we'll expand that. But aromatic means benzene with 3 double bonds. We only have 1 double bond. Okay? What does the next one show?
It's still gonna show the carbon-carbon.
Carbon-carbon double bond, single bond,
It's gonna show the same stuff.
and the last one.
It's gonna show everything the same.
Okay, well, we can at least prove what using our IR.
It's happening.
We formed a double bond. What else could we look for to help us go like, yes, we did form a double bond?
Water, formation of water.
If we have any water there, that's going to wash out our entire sample. We're not going to see anything. All we'll see is water. The alcohol. Do we have the starting material anymore?
No.
No. So theoretically, when we run the IR, what we'll look for is the lack of NOH. We can also look for the lack of, much less likely to look for this, the CO. Why would we be less likely to look for the CO? It's in the fingerprint region. It's very easy to get confused with other signals. So I wouldn't stress necessarily about the CO, but we should expect to see the lack of the OH. So that can help us prove that we at least did an elimination. Doesn't tell us that we formed any one of those products.
No.
No. Right. In a larger lab environment, what we would do is take our product and we would test it using a fancy chromatography apparatus to see how much of each of those products was formed. Unfortunately, the version of the apparatus that we have here does not detect these. So we can't do that. Right? So I had to come up with some other way to detect these potential products. What we'll do next week is we will then react those structures with more compounds. Would we expect different reactions out of these? Why?
Because aren't you creating like a secondary, primary, secondary, tertiary?
We have the double bonds located in different positions, which could evaluate different speeds of a reaction. You all enjoy doing speeded timed reactions, right?
Oh, yeah.
Yeah, so we'll avoid that. But we have different chemistry at each of those 2 positions. At one position we have a methyl, so that carbon could be kind of closely sort of referred to as tertiary versus secondary. officially kind of tertiary versus primary. It's attached to one other carbon.
He's worried now.
Secondary because it's connected to two carbons, and
Secondary.
secondary because it's connected to two carbons. So we could actually expect to see a difference in the products that come out of this. So that's what we'll do next week, is we will react the double bond with a couple different systems, a couple different environments. We'll then test those products as well to see if we can identify where reactivity went, okay, or where our chemistry is occurring. To do that, that means you're going to have to be told how the next reaction is working. And I will tell you that. This reaction you're not getting told, sort of. Okay. We have 3 different products. We don't necessarily know which product is going to be formed. Right? This has been studied time and time again by a relatively famous person known as Zaitsev. Okay? They'll come up with Zaitsev's rule. Right? Part of this assignment is that you're going to do some research on Zaitsev, and that's going to show up in your report. Okay? So that you know what the rule is. If you want to get a jump start so that you know what your product is, that's fine. Just be very, very careful in this. You will be graded on how you analyze your results. If your results tell you that Zaitsev was wrong, you better not tell me that you prove Zaitsev was right. Make sense? So you have to make sure your results reflect what you're concluding. And that's going to be a big part of the discussion. Nothing is due while you get the prelab next week. So you'll have your prelab. I am working on getting that finished. I'm hoping to have that done by tomorrow night. So all of this is material on determining what our product was. We, in theory, know all of this before we went into lab. So all of this needs to show up in the introduction. Okay. Each of these stages, we discussed different parts that were problems, things that we needed to fix and adjust and prevent from happening, or potentially allow happening. You need to explain why each of those things are happening or not happening. What is good, what is bad, how does that get us to our products? You could potentially even throw down in your introduction, this first product formed out of how many different pathways? 1, 2, 3 pathways made this product. How many pathways made this product? 1. How many pathways made this product? 1. Careful. 2 pathways made that one. So we're looking at maybe 3 times, 1 time, 2 times the amount of products coming out of each of these. Okay. And that's partly what we're trying to look at, is piece together how this could come out. Kind of make sense? Okay. The next question is, how do we go through and do all of this? So this is the chemistry that's now happening in our reaction flasks, but how? Where is our reaction flask? How are we isolating these products?
Distillation.
We're going to run a distillation, which is going to do a couple things for us. Number 1, to distill, what do we need? Heat. Why might heat be important for this reaction? We needed to break that carbon-hydrogen bond. So we're now providing heat that will facilitate that breakage. Okay. Why distillation, though? Why not just add heat and then work it up afterwards? How is it going to separate? What are we separating?
The crude product.
All of our products are roughly going to come out at the same boiling point. You can even test that to verify. The alcohol needs to be separated away from your alkenes. That's also going to be how we're going to determine that you did a decent job. If you don't separate the alcohol away, you're going to see the OH in your IR, and that's going to suck. You didn't do a good job purifying. So why would distillation work to separate those? Why are their boiling points different? What about their intermolecular forces? The alcohol has hydrogen bonding, and your products all have London dispersion forces. Which one has the weaker force? The LDF, or London dispersion. Our alkene has the lower product, so as soon as it is formed, as long as we're adding heat, what does our product then do? Evaporate. Oh crap, now we've lost it.
We can never see it.
We can then collect that and distill it back out. So that's how we're going to end up isolating our product. Are we going to get just pure product distilling out? Why not?
You're gonna get water.
One of our byproducts in this reaction is water. We will have acid, which brings up an interesting issue. If there's water present and we add a dilute acid, what happens? If this is equilibrium and I have a large concentration of product, what happens? Shifts backwards, which means the acid that I add had better be concentrated. If it is dilute, the equilibrium is actually going to push to prevent the formation of product because we have a large concentration of water byproduct. So we want a concentrated acid added in there. Issue with concentrated acids, they burn stuff, okay? And it will result in the loss of some product and starting material because it's burning through it. That's fine, we just kind of accept that as a loss. But we will need to use a concentrated acid to minimize the presence of water. Now your question.
Yeah, water's concentration doesn't change.
Water's concentration does not change in Gen Chem because
Liquid.
it's the solvent. Is water our solvent? No, the concentration of water will change throughout the course of the reaction. Okay. So we do produce water. And the presence of water is going to do what? Reverse the reaction. So we want to minimize water by using concentrated, okay, sulfuric acid. The next issue is that that water that is produced, should it mix with the alkene? No. Which means our distillation is two phases, technically a heterogeneous distillation. A heterogeneous where one of those phases was water, which means we're not doing just a standard distillation, we're doing a steam distillation, believe it or not. Okay? Not intentionally, but that's how it's going to end up working out. Water is also going to distill across with our product. Okay? The presence of water can reverse the reaction. Okay? But in theory, for that to work, we will also need the presence of an acid. The acid boiling point really, really, really high, so we'll have a relatively minimal concentration of acid, so that should prevent the reaction from occurring on the far right, okay, or once we've distilled it out. But this means in our distillation pot we'll have water and the alkene. How do you get rid of the water? Sodium sulfate, drying agent. Right? If we look through the procedure, is that all we're adding? Are we just adding sodium sulfate? No, what else are we doing? Bromine's not there yet. We're doing sodium bicarbonate. Do we do sodium bicarbonate first, or do we do water first?
Sodium bicarbonate and then sodium sulfate.
So bicarb, then sodium sulfate? Okay. Sometimes we throw water there. Why bicarb first?
That's a brine?
Bicarb is not a brine, it's actually a base. Why are we adding a base?
Neutralizing the extra acid.
Some acid may carry across, not a lot, but some will. Okay? We want to neutralize that acid, because what are we going to do with it? Throw it away. Our waste should be neutral when we go to throw it away. The more acidic or basic it is, we now have to pay someone to neutralize it. So we're adding a little bit of bicarbonate to reduce the cost, effectively, of our waste disposal. It also increases safety. Why? You won't get burned if you spill it on yourself, because you've now put the base on it to neutralize it. Make sense? Right. We can then go through, remove that, like we would as a normal wash. We add it, mix it around, and then remove it. Okay, which layer is which? So should the water be on top, or should the alkene be on top? How do you figure it out? Look up the densities. We all did a prelab where you look down the densities, right?
Yeah.
Right. You'll notice that in the prelab, I think I even included some names for compounds that you needed to get, because most people tend to forget looking up the products.
Mhm.
Okay, so that's why they were there. Hopefully you've got those densities. Anybody have them? What was the density?
0.8.
0.8, which means,
It's on the top.
where's water gonna be? Water's density is 1,
One,
which means
it's heavier.
it's heavier, so water's on the bottom.
So it's gonna be
Yeah,
on top.
okay, sorry, I thought I heard something else. So we got our product on top. Pipette the water layer out, then what do?
You say it next week.
The bottom layer is water. We'll do the drying agent to fully remove all the excess water, so we'll have our pure product left over. Okay, make sense? With that pure product, you then need to get a weight once you've removed the drying agent and an IR. Okay? Both of those, weight you'll use for determining your percent yield, how effective you were in the experiment. The IR you'll use to prove as part of your analysis that you actually did the elimination reaction. We don't know which elimination reaction you do, but we've got evidence that you did it at least. Just a sec, go ahead.
So what is in the brine? The procedure continues to reference the brine solution.
Oh,
What
see,
is actually?
I didn't hear anybody say brine, so that's why I mentioned it. You do bicarbonate, then you do
The brine.
brine, and then you do drying agent.
Yeah.
So brine we do before the drying agent, because the brine will remove more of the water. So trapped out on the ocean, what do? Or what do you not do? Drink ocean water. Why?
It's salt.
It's salt in it. What happens with briny solution? It pulls moisture out of whatever solution is nearby via osmosis. So the brine we'll use to remove the bulk water. Right? It'll also help shift some of our organic product that might be slightly soluble in the aqueous layer into the organic. I guess into the organics the other direction. Then you can remove the brine and add your drying agent to remove the last remnants of water. Right? With drying agent, how much do you add? Till it stops clumping. We have to be careful with the definition of clumping. Okay? Get in there, stir it around a little bit. You should see single crystals or some single crystals. Some clumping is okay, it will happen, but you should be seeing single crystals. No more than half of your total volume should be drying agent. Okay? That's pretty much your maximum. Before you even add drying agent, check and look at your liquid. Do you see 2 layers? If you see 2 layers, you are not adding drying agent. You are removing that second layer. Okay? You should not see 2 layers before adding drying agent, because one of those layers is water, and water won't absorb enough into the drying agent if it's visibly present. Okay? So you need to make sure you have one visible layer before you add drying agent. You can remove the drying agent just by pouring. The liquid will pour out nicely into a separate container. I'll track down some containers so we can store those for next week. Whatever product you've got, hopefully in the gram to 2 gram range, will be enough for next week. And next week we'll end up doing asymmetric addition reactions with our alkenes to hopefully be able to predict which product we formed in preference to the others. And your question is?
At the end of the experiment, where do you want us to put our product?
Where do you want to put your product? We'll get you a little vial, cap that vial, put your name on it, and then you can actually give it to me, and I'll stash it up in the front so it doesn't get involved with Wednesday's stuff.
We're still doing that in saturation test.
There was another test. Right? We have another test to verify that you made an alkene. Is the reactivity of an alkene different than an alcohol?
Yes.
Yes. So what we're going to do is test that. Okay? We'll do what's known as a classification test. In fact, some of the experiments we're doing next week are classification tests. They are designed, very, very old school, to test very, very quickly that a functional group is present. Okay? The one that you are going to test is your alkene in the presence of bromine. The result, which again we'll talk about next week because I don't want to bring in addition into this. Let's just pick with that last one. Is the bromines, the 2 bromines will split and add to the double bond. That's it. Okay. What color is bromine? Okay. It's a red-brown. What color are alkyl halides? Clear. So we can verify that something reacted with the bromine by adding our red-brown bromine to a drop of your final product. If the solution goes clear, what does that mean? Something reacted with the bromine, more than likely, double bond. You now have evidence that a double bond was formed in the reaction. Again, do we know which double bond?
No.
No. All we know is that a double bond was formed. Make sense? Okay. So at this stage, we're really just testing at the base level, do we have enough evidence to say an elimination reaction occurred? That's what we're hoping for. Yes is the answer to that at the end of the day. Okay. Because we've got the lack of the OH, okay, we've got the presence of our carbon-carbon double bond, okay, in our IR, and we have the results from our unsaturation test. Okay. The end of next week, hopefully we'll be able to go back and say one of those is our primary product. That is the goal. Yes?
You say primary, so next week we should also expect to see mixtures of, well, you said like one.
So that's a good question. When we run this reaction, is there any guarantee that we only get one of these?
No.
We could very easily get all three. What is that going to do to our potential results next week? Okay. Could very well convolute and confuse the stuff out of it.
Which is why you're saying that the report really has to reflect all the fine.
Exactly right. So some people get very clean results, some people don't. Right? I don't care necessarily about the results, I care about your analysis of the result. Okay. Questions? Okay. Stop.